You've definitely interacted with them. I mean, helpful virtual assistants, those powerful writing tools, even, the customer service chatbots we bump into online. AI chatbots are really fundamentally changing how we communicate, how we get information. But have you ever stopped to wonder what's like really happening under the hood? What's the digital architecture making them seem so, well, intelligent?
Yeah, and that's really what we want to unpack today. In this deep dive, we're going to pull back the curtain on the core technologies that power these systems. That includes things like the large language models or LLMs you hear so much about now. We'll explore how they work, why they've kind of revolutionized AI, and also what big challenges are still out there. Think of it as maybe your shortcut to understanding the digital brains behind today's AI.
Right, so to really dig into what makes these impressive systems tick, we need to start with the foundations, right? Often when people talk about the brains behind modern AI, you hear these two terms again and again, deep learning and neural networks. Why are they so central?
Well, deep learning, which is
Hmm.
powered by these deep neural networks, it's really the engine behind the huge leaps we've seen across AI lately. And it's not just language, it's powering everything from, say, facial recognition to mastering really complex games like Go.
And these neural networks, they're sort of inspired by the human brain, aren't they? How should we visualize them?
Yeah, loosely, imagine a neural network as a whole series of interconnected layers, computational layers. Information flows through them, gets processed in stages. It's a bit like signals cascading through neurons in a biological brain.
Hmm.
And that multi-layered structure, that's the deep part of deep learning. It's what lets these systems find really complex patterns, abstract features in data.
It's pretty wild that neural networks, which are so key today, actually go way back to the 1950s.
Hmm.
And they had this controversial history, even fell out of favor for a while. What
Hmm.
what brought them back, especially after all that early skepticism?
That's a great point because it wasn't just one thing. Their huge comeback in recent decades was really a perfect storm. You had massive investment from the big tech companies, Google, Facebook, Microsoft, you name it. And crucially, you had huge advancements in specialized hardware. We're talking about modern GPUs, graphics processing units from companies like NVIDIA. That combination let us train much, much deeper, more complex networks on just enormous data sets. And that directly led to this deep learning revolution.
Okay, so deep learning is the engine, but how do these systems actually understand something as complex as human language? Because, I mean, for a computer to even start processing language, it needs to turn words into numbers first, right?
Exactly. That's the first hurdle. Convert words into some kind of numerical form. Now, there are basic ways, like giving each word a unique, very long numerical ID, kind of like a giant list. But the real breakthrough came with something called word embeddings.
Ah, word embeddings. Okay, this is where it gets really cool, isn't it? Because it's not just giving a word a number, it's giving it a number that somehow captures meaning.
Precisely. Word embeddings are these sophisticated, multi-dimensional numerical representations. And the key idea is that the semantic distance, basically, how similar words are in meaning or how they're used in context, is directly reflected by the geometric distance between their points in this numerical space.
So wait, words like king and queen, or say cat and kitten, would actually be mathematically close together in this space.
That's exactly right. Words with similar meanings or words that tend to show up in similar sentences, they end up numerically closer. And this lets AI systems do some pretty surprising things, like solving analogies. You can literally do math with these word vectors. Take the vector for woman, subtract man, add king, and the closest result in that embedding space. Often it's queen. It's
Mhm.
almost like the system is learning these mathematical relationships between concepts, not just memorizing words.
Wow. Doing math on meaning. That's,
Man.
that's kind of mind-bending. But I imagine, like any powerful tool, it probably has its quirks. Does this embedding method ever give weird or nonsensical results?
Oh, absolutely. It definitely can. While it's powerful, you sometimes get these cryptic or just plain nonsensical associations. Like one example someone found was transforming thirsty is to drink into tired is to drunk, which, yeah, it really highlights the statistical nature of how these things learn. They find patterns, strong correlations in the data, but they don't necessarily grasp human-like cause and effect or, common sense.
That's a perfect lead-in, actually, because understanding single words or even their relationships, that's one piece. But language is all about sequence, right? The order of words, the flow. That needs a different kind of neural network, doesn't it?
It does, and this is where recurrent neural networks, or RNNs, really made a difference. They're specifically built to handle sequences of information, words in a sentence, characters in text, even notes in music. The order of information is absolutely critical here. It changes the meaning completely as you go.
What's always fascinated me is how RNNs manage to remember stuff from earlier in the sequence.
Yep.
How do they hold on to context without just getting swamped by everything that came before?
They use these special components, often called gated units. Think of them like tiny, sophisticated memory cells. But crucially, they actively control the information flow. These gates can decide to selectively hold on to important context from earlier, while maybe letting go of stuff that seems less relevant. It's like a managed memory. This allows the network to keep track of things over longer stretches of text. So, for example, in sentiment analysis, the network reads a sentence word by word, building up this internal representation, this encoding as it goes. Then it uses that accumulated information at the end to decide, say, if the overall feeling was positive or negative.
Okay, so it sounds like putting these pieces together, the deep layers, the meaningful word embeddings, the sequence memory of RNNs, that really kicked off a new era for AI, especially with language. What were some of the big moments or shifts that really showed this revolution was happening?
Well, applying deep learning to language just led to breakthroughs people thought were maybe decades away. Machine translation is a huge one. Historically, that relied on these super complex, handcrafted rules. Very brittle, often didn't quite capture nuance. But then neural machine translation came along. Systems like Google Translate got so much better, people started talking about bridging the gap between human and machine translation. Some companies, like Microsoft, even claimed they reached human parity for translating certain language pairs, at least in specific controlled
Yeah, I
contexts.
remember that. And it wasn't just translation either. Thinking back to IBM's Watson on Jeopardy back in 2011, that felt like a massive moment, showing it could understand, colloquial questions and pull answers from huge amounts of data super fast.
Definitely. That was a big milestone for question answering systems. And beyond translation and Q&A, deep learning also massively improved automated speech recognition. It's why our voice assistants, on our phones or smart speakers, are generally so much better now at understanding everyday speech. Though they still mess up sometimes, right? Especially with background noise or like unusual names. I remember trying to dictate a shopping list once, and my phone insisted on turning avocados into advocates for dogs. So, yeah. It kind of reminds you their understanding is still statistical, not quite like ours.
Right. Advocates for dogs. That's a good one.
Yeah.
And while we focused a lot on language today, it's important to remember these deep learning advances weren't just about text, were they? How did this revolution affect other AI areas?
Oh, absolutely. It's spilled over everywhere. In computer vision, for instance, deep learning models called convolutional neural networks, or ConvNets, combined with huge image datasets like ImageNet and those powerful GPUs we mentioned, they just dramatically improved object recognition.
Mhm.
Suddenly, AI could identify and categorize millions of images with pretty high accuracy. That was a real game changer.
And then there's game playing.
Yeah.
The progress there has been just astonishing. Seeing AI master games like Go, which seem to rely so much on intuition and deep strategy.
Totally. The deep Q learning approach that's combining reinforcement learning with neural networks that led to AlphaGo beating Lee Sedol, the world Go champion, a landmark moment. And what was maybe even more impressive were the later versions, like AlphaZero. AlphaZero learned to master chess, shogi, and Go just by playing against itself. No human games, no opening books initially, just learning from scratch. It showed this incredible ability to discover complex strategies and reach superhuman levels in these very defined, rule-based domains.
So we've walked through these incredible breakthroughs, but like any big technological shift, there are hurdles. Let's get into the reality check now. What are the big limitations these powerful systems are still facing? First one seems obvious. They need so much data.
That's a huge one. It's a fundamental constraint right now. For all their power, today's deep learning systems require absolutely massive amounts of training data. And often, that data needs to be labeled by humans. You hear prominent AI researchers talk about this all the time. Andrew Ng called requiring so much data a major limitation. Yoshua Bengio noted, we can't realistically label everything in the world. This dependence on vast curated data sets is a real bottleneck. It limits where and how easily we can deploy these systems.
And linked to that, perhaps, is the black box issue. We hear this term a lot. These systems are often called black boxes because you can see the input, you see the output, but the reasoning, the steps in between,
Yeah.
they're not really transparent, are they?
No, not usually. And what's really fascinating and kind of critical to grasp here is why they're black boxes. These machines are incredibly good at finding statistical patterns, correlations in the data they're trained on, but sometimes those patterns are totally irrelevant to what we want them to learn. They might latch on to spurious correlations. This isn't just a theoretical issue. It shows they often operate without, let's say, true causal understanding. Their decision making is opaque and worse, potentially unpredictable when they encounter new situations. This can lead to some really weird failures, like an image recognizer focusing on blurry backgrounds because that's what correlated with a certain object in the training set, not the object itself. Or maybe more worryingly, they can be tricked by adversarial attacks. Tiny changes to an image, invisible to us, that cause the AI to completely misclassify it. Think a stop sign seen as a speed limit sign, or worse, a medical scan wrongly flagged. The key takeaway is their intelligence is fundamentally statistical. It's not based on a deep, intuitive grasp of the world like ours. And that has huge implications for trust, especially in high-stakes applications.
So they're not really understanding in the way a human does then, which leads us to maybe the biggest gaps. Common sense, reasoning, abstraction, generalization.
Exactly. You might be surprised given how powerful they seem, but current deep learning systems really struggle with what we consider basic intelligence. Take common sense reasoning. An AI might totally flub a simple question like, if you move a plant from a dark corner closer to the window, will its leaves likely grow faster or slower? It lacks that vast background knowledge about light, photosynthesis, plants, stuff a kid picks up. That's a massive hurdle for anything approaching human-like AI.
And it's not just common sense. There's also this issue of transfer learning, or maybe the lack of it. A system can be superhuman in one specific game, but if you change the board size slightly or tweak the rules just a bit, it completely falls apart. It needs retraining from scratch.
That's often the case, yeah. It really highlights a fundamental difference. Humans are great at taking knowledge learned in one context and applying it, adapting it to new, even slightly different situations. We don't usually have to start over completely. Many experts in the field stress this. Deep learning is an incredibly powerful tool, absolutely revolutionary. But it's likely just one tool in the toolbox needed for artificial general intelligence. Achieving human-level intelligence probably requires much more robust reasoning, deep background knowledge, genuine common sense. Figuring out how to instill those qualities in machines, that remains one of the biggest open challenges in AI today.
So wrapping up our deep dive today, you've gotten a look under the hood at AI chatbots and the technologies like LLMs that power them. We've touched on how they turn words into meaningful numbers using embeddings, how recurrent networks handle sequences, and how tons of data and computing power led to breakthroughs in translation, game playing, and more.
hmm But we've also seen the significant limitations they still face. That huge appetite for labeled data, the black box problem, making them hard to trust and debug. And their fundamental struggles with common sense, with abstract reasoning, and with truly generalizing knowledge to new situations like humans do.
The journey towards truly intelligent machines is definitely ongoing. You hear predictions that human-level AI is just around the corner, but then many others believe we have a really long way to go, especially to replicate the subtle, flexible, common-sense intelligence humans possess. So it leaves you with a big question, doesn't it? As AI keeps evolving, are we on a path to build systems that can genuinely think and reason like us? Or will they always be incredibly sophisticated pattern-matching machines, just, faking their way towards understanding? Something to think about.